Okay, so in this section, it's the interpretations and applications of the derivative and definite integral. So what we're going to be doing is take what we know about derivatives and integrals and applying them to problems. Okay, so in our example here, d dx, so the derivative, is the rate at which the amount is changing. So always remember that derivative is rate. For example, if water is being drained from a swimming pool, and R of t represents the amount of water, measured in cubic feet, that is in that swimming pool at any given time, measured in hours, then R prime of t would represent the rate at which the amount of water is changing. So what would the units of R prime of t be? Well, if we're talking about the rate, okay, then R prime of t would be feet cubed per hour. Okay. The integral of the rate is the amount of change. So in the context of the example situation above, explain what this value represents if we integrate R prime of t. Okay. So if R prime is the rate at which the amount of water is changing, then to take the integral of that is the amount of water that's actually in the swimming pool. Okay, so this represents the amount of change in the water. From time equals A to time equals B. So the table given below represents the velocity of a particle given at values of t, where t is measured in minutes. Approximate the value of the integral from 0 to 30 using a midpoint Riemann sum. Using correct units of measure, explain what this value represents. So it doesn't tell you the width of each of the rectangles, so I'm just going to take the width to be these. So the distance from 0 to 10 is 10, 10 to 20 is 10, 20 to 30 is 10. So if we're taking midpoint, I'm looking at these values here. So the integral from 0 to 30 of v of t dt is equal to the base times the height of each of these rectangles. So 1.6 plus 3.1 plus 1.6. And you add all that up, and that's 63 feet. Okay, so what does this actually represent? Well, if we're talking about a particle and we are integrating velocity, then this is the position. Okay, so what this represents right here, as we learned in the last section, is net distance. Okay, so if we look at part B, what is the value of the integral from 5 to 25 of a of t? Well, if we integrate a of t, that's the same as saying v of 25 minus v of 5. Okay, so v at 25 is 1.6 minus v at 5 is 1.6 as well. So this equals 0. And then if we're talking about acceleration, or I'm sorry, velocity, it's feet per second. Okay, so what does this represent? So if we are integrating acceleration, we have velocity. If the velocity is 0, this is the change in velocity of the particle. So if it's 0, this means that the particle is not changing velocity. So if we look at the next one, the temperature of the water in a tub at time t is modeled by a strictly increasing twice differentiable function w, where w of t is measured in degrees Fahrenheit and t is measured in minutes. So they've given you a table. Using the data in the table, estimate the value of w prime of 12. Using correct units, interpret the meaning of this value in the context of the problem. So if they ever say estimate and you have a derivative, you guys should be recognizing that it means use the slope formula. So w prime of 12. Well, I don't have a 12 in my table here. So I'm going to look at this value and use my slope formula. So w of 15 minus w of 9 over 15 minus 9. So we have 67.9 minus 61.8 all over 6. Okay, which if you do that calculation, you get 1.017. And your units, I can't even read my own handwriting here, would be degrees per minute. Okay. So what does this mean in the context of the problem? Well, since w prime of 12 is greater than 0, so since this is positive, the temperature is increasing. Okay, so the next one, use the data in the table to evaluate the integral from 0 to 20 of w prime. Using correct units, interpret the meaning of this integral in the context of the problem. So if we are integrating the derivative, that's w of 20 minus w of 0. We just go backwards. Well, w of 20 is 71.0 minus w of 0 is 55.0. So this equals 16 degrees Fahrenheit. So what we just did to integrate a derivative is the same. So if w represents w of t is the temperature of the water. So w prime of t is the change in the temperature. So if we integrate that, this represents the amount of change of the temperature of the water. Okay, so last one. For t is between 20 to 25, the function w that models the water temperature has a first derivative given by the function w prime of t. Based on this model, what is the temperature of the water at time t equals 25? Okay, so we want to know the temperature of the water. So we want to know w of 25, but we have w prime. So this is where we use the fundamental theorem of calculus to integrate. Instead, we are going to go from 20 to 25 of w prime of t dt. Based on what we know from the fundamental theorem of calculus, this is equal to w of 25 minus w of 20. So since we're given an actual equation for the derivative, we can evaluate this integral over here. Okay, so you will find this integral is equal to 2.043. We want to know w of 25. We already know w of 20, which is 71.0. So do some algebra, and you get that w of 25 is equal to 73.043. Okay, and we also need units, so we need temperature, so it says degrees Fahrenheit. So in this one, a pan of biscuits is removed from the oven, at which point in time, t equals 0 minutes, the temperature of the biscuits is 100 degrees Celsius. The rate at which the temperature of the biscuits is changing is modeled by the function b prime. Find the value of b prime of t using correct units. Explain the meaning of this value in the context of the problem. So at this point, we're just plugging in 3 for b prime of t. So if you use a calculator, you will find that this is negative 8.236 degrees Celsius, per minute, because we're talking about a rate. So this is the rate at which the temperature of the biscuits is decreasing. And how do you know that it's decreasing? Well, the rate is negative, okay? Sketch a graph of b prime of t on the axis below. Explain in the context of the problem why the graph makes sense. So if you graph b prime of t, you should get a function that looks something like this. Okay? So this is the derivative of b prime. Okay? It is always negative. Well, if the derivative is negative, that means that the original function is decreasing. So since b prime of t is less than 0 always, the temperature is always decreasing. So now at time t equals 10, what is the temperature of the biscuits? Show your work. Okay, so we want to know the temperature, so we want to go backwards, we want to integrate. We are given this initial condition up here. At time t equals 0, the temperature of the biscuits is 100 degrees Celsius. So in our integral, our boundary is going to be from 0 to 10, b prime of t dt, and that's equal to b of 10 minus b of 0. So now if you use your calculator, because you have an equation for b prime of t, you get that it equals negative 65.817. We don't know what b of 10 is, but we know that b of 0 is 100. So doing some algebra, you get that b of 10 is equal to 34.183 degrees Celsius. So last and final example. A cylindrical can of radius 10 millimeters is used to measure rainfall in Stormville. How creative of a name. During the first 5 days of the 60-day period, 3 millimeters of rainfall had been collected. The height of the water in the can is modeled by the function s, where s of t is measured in millimeters and t is measured in days, for t between 5 and 60. The rate at which the height of the water is rising is given by the function s prime. Okay, so remember this is a rate. Find the value of the integral from 10 to 15 of s prime. Using correct units, explain the meaning of this value in the context of the problem. So if we want to integrate this, that's the same as saying s of 15 minus s of 10. Okay, so s of 15, what do we know? So since we have the equation, we can just do this calculation. So on your calculator, you should get 11.159, and your units are millimeters. So if this is the rate of the rainfall, the s prime of t, to integrate that is the change in the water level. So we have the change in the water level from t equals 10 to t equals 15. At the end of the 60-day period, what is the volume of water that had accumulated in the can? Show your work. So it wants to know the integral. So up here it says during the first 5 days of the 60-day period, 3 millimeters of rainfall had been collected. So that's kind of an initial value. So this says that S of 5 is equal to 3. So we can use that in our integral. We can go from 5 to 60 of S prime of t dt, and this is equal to S of 60 minus S of 5. So it wants to know at the end of the 60-day period. So it wants to know S of 60. So using our calculator, we can figure out this integral. You should get 163.565 is equal to S of 60 minus, we already know S of 5 is 3. So that means that S of 60 is equal to 166.565. And units would be millimeters. So S represents the height of the water in the can, but we want to know the volume. So volume of a cylinder is pi r squared h. Okay, it already gives us the radius. It is 10 millimeters. And our height is this S of 60 here. So if you do some calculations, you will get 16,656.488 pi. And this is millimeters cubed. Okay, so the last and final one, the rate at which people enter an auditorium for a concert is modeled by the function r. So r is a rate given by r of t. R of t is measured in people per hour. VIP tickets were sold to 100 people who are already in the auditorium when the doors open at t equals 0. So the number of people in the auditorium at the very beginning is 100. The doors closed and the concert began at t equals 2. If all of the VIP ticket holders stayed for the concert, how many people are in the auditorium when the concert begins? So it wants to know the number of people. We are given the rate at which people enter the auditorium. So we need to integrate that. So we know that time starts at 0 and the doors close at t equals 2. So we set up our integral from 0 to 2 of r of t. So we know r of 0. We don't know r of 2. Okay, so whenever the doors open at t equals 0, there's already 100 people in there. We want to know how many people are in the auditorium when the doors close. So r of 2 is what we're looking for. So if you do some math on your calculator, use this integral, use the equation, you should get 980 is equal to r of 2 minus 100. If you solve for r of 2, you should get 1,080 people. So this section is just about applying what we know about derivatives and integrals. Okay, so let me know if you guys have any questions.